welcome the Senior VP of AWS Infrastructure and Support, Infrastructure Leadership, Peter DeSantis.
Good morning. Thank you for joining me. For those of you who have not watched this keynote before, we like to go a little deeper on how AWS thinks about and builds infrastructure. This morning, I have some pretty cool things to share. Hopefully by now, you've heard about Graviton2, as customers are reporting some fabulous results, both improving their performance and lowering their cost. Today, I'm going to show you how we designed Graviton2 and why it performs so well. And I'm excited to give you an update on our progress on sustainability. We've made a ton of progress since last year, and I can't wait to share that with you either. Of course, I have some really great customers here to talk about how they're using AWS infrastructure to do amazing things for their customers. But I want to start off this morning by talking to you about something a bit different, how we operate. Can you tell me how AWS operates? This is a question that I often get from customers. And they usually ask the question for a couple reasons. First, they want to understand our operational practices. Because if you're going to run your critical workloads in the cloud, you want to know that you can depend upon the operational practices of your cloud provider. But customers also ask this question because they want to see what they can learn from AWS and apply those learnings to their own business. At Amazon, we pride ourselves in being a little bit peculiar. And one of the ways this comes across is in the way some leaders express their ideas. I've been collecting these peculiar quotes for over a decade. You see, it's part of my retirement plan to write a book on Amazon culture. Unfortunately, that book is not coming along that quickly. So I thought it might be fun to use a few of these quotes to help us along in this discussion. Let me start with one of our favorites. When it comes to being a great operator, there's no shortcuts. Great operational performance is the result of a long-term commitment and an accrual of small decisions and investments compounding on top of one another. But I do think there are a few things different about the way we approach availability at AWS. And I think it starts with AWS growing out of Amazon. Amazon is at its heart a technology company that's uniquely tied to the physical world. Operating warehouses and customer support centers, running a complex international supply chain, and keeping a website up 24 hours a day, 7 days a week for decades. These are all real-world operational challenges that benefit from technological invention. And these problems have inspired us to be both great technologists and great operators. Here's an interesting quote from a leader that must have been a big fan of Columbo, or perhaps the board game Clue. But what's interesting about this quote is the context. This leader was patiently sifting through the details to find the root cause of a problem. And now when I interview senior leaders from other companies, they often ask me, is there common challenges that are faced by new leaders at Amazon? And I tell them the most common reason that I see new leaders at Amazon struggle is not getting into details the way we would expect. We expect all our leaders, however senior, to spend a considerable amount of their time working in the details. If you're an engineer, it's nearly impossible to build a high availability system without understanding the operational challenges encountered by the current systems. And if you're a manager, it's difficult to make informed decisions about things like roadmap without understanding these same details. Setting the right culture and being in the details matters. But if you want to provide your customers with differentiated operational performance, you need to design it in. You may have heard Werner Vogel say, everything fails. And that idea, that anything can and will fail, influences everything we build at AWS. The idea is simple. Anticipate failure and design your products to protect your customers. To illustrate this idea, we'll look at how we build our infrastructure, specifically our data center power infrastructure. Let's start with the basics. These are the usual suspects involved in high availability power design. There's a utility feed coming into the data center. Power from the utility goes into what's called switchgear. This is really just a set of interlock breakers with some monitoring logic and control logic. Our switchgear here is responsible for detecting when there's a utility power issue, and when it sees this, it disconnects the utility power and it activates a backup generator. the power from the switchgear is fed into what's called an uninterruptible power supply, or UPS. A UPS is essentially an energy storage device that supports the critical load while the switchgear switches between the utility and the backup generator. Now, while this is a simple design and it works for utility failures, this comes up far short of what you need to run a data center. Let's take a look at that. We'll start with a generator. Generators are big mechanical systems, and they sit idle most of the time. But for the handful of minutes you need them every few years, they really need to work. Now, with the right preventative maintenance, they're remarkably reliable. But remarkably reliable isn't good enough. At scale, everything fails. And to keep your equipment running at its best, you need to do preventative maintenance. And to do this maintenance, you have to take the generator offline. And while it's offline, it's not there to protect your critical load. So you have to add a backup generator. This concept, called concurrent maintainability with redundancy, is important for all of our critical gear. So what can we do? Well, we add another generator. This is a fairly easy change, but we still have problems with this simple design. What happens if the UPS or the switchgear fail? And how do we do maintenance on those components? Let me show you how we think about different components in a system and their potential impact on availability. When you look at the components of a system, whether they're systems in a software system or a physical system like the one we're looking at here, it's useful to think about them along a couple dimensions. The first is, what is the blast radius of the component if it has a failure? If the impact is really small, then the failure may be less of a concern. But as the blast radius gets bigger, things get much more concerning. And in the case of our power design, the blast radius of both components is big, really big. Data center UPSs these days tend to be around 1 megawatt of power. To put that in perspective, you can power thousands of servers with 1 megawatt of power. And your switchgear, it needs to be at least as big as your UPS, and it's often much bigger. So both of these components have big blast radius. The other dimension that's interesting when you're evaluating components is complexity. The more complicated a component, the more likely it is to have an issue. And here, the switchgear and the UPS are quite different. Let's take a deeper look. As I mentioned, switchgear is fairly uncomplicated equipment. It's big and super important, but it's really just a bunch of mechanical circuit breakers, some power sensing equipment, and a simple software control system. Now, that control system is simple, but it is software. Most vendors will refer to it as firmware, but that really just means it's embedded software that gets saved to a persistent memory module. And software that you don't own, that is in your infrastructure, can cause problems. First, if you find a bug, you can spend weeks working with the vendor to reproduce that bug in their environment. And then you wait months for the vendor to produce a fix and apply and validate that fix. And in the infrastructure world, you have to take that fix and apply it to all these devices. And you might have to send a technician to manually do that. And by the time you're done, it can easily take a year to fix an issue. And this just won't work to operate the way we want. Another problem with third-party embedded software is that it needs to support lots of different customer use cases. Vendors need to optimize their equipment for what most of their customers want, not what you need. And this means added complexity, which in turn increases the risk of a failure. And finally, small operational differences in how the different software behaves can make your operations different, more complex, and this can lead to mistakes. So many years ago, we developed our own switchgear control system. We call it AMCOP. You can see it pictured here. Now, this may look fairly simple, and indeed, we've invested heavily in keeping it as simple as possible. We don't add fancy features to our controller. Instead, we focus on assuring it does its very important job perfectly. Today, we use dozens of different makes and models of switchgear from several partners, but they're all controlled by AMCOP. And this means that we can operate our global data center exactly the same way everywhere. Now let's look at a UPS. There's lots of ways to spot complexity. The first is to look at how many components are in the system. And you can see from this picture that UPSs have very complex electronics. But what you can't see in this picture is the software that runs on these components. And that's where things get really complex. The UPS has a hard job to start with, and vendors have jam-packed the UPS with features over the last 20 years. Now, we often disable many of these features, but they still add complexity to the UPS. Beyond the complexity of the UPS itself, they're batteries. UPSs need to store energy somewhere, and they usually do that in lead-acid batteries. There are other solutions, but lead-acid batteries have an advantage of being an old, well-understood technology. But they have disadvantages, too. The batteries for a single 1 megawatt UPS weigh 12,000 pounds, and they're best stored in a dedicated room because they require special environmentals. All right, let's go back to our chart. As we saw earlier, both the UPS and the switchgear are big. But the UPS is significantly more complex. So let's update our chart. Okay, now you can clearly see what's keeping us up at night. And we're not the only ones that have come to the conclusion that a single UPS is not reliable enough. Lots of smart people have worked on solutions. There's no standard solution, but the common approach is to throw more redundancy at your design, usually by adding a second UPS. And often this is done by using a feature of the UPS that allows it to be paralleled with other UPSs. The problem with this approach is that it doesn't really change your position on our graph. You still have a big, complicated component keeping you awake at night. You've just added one more, and it's connected to the other UPS. More interconnected, complicated components is seldom a solution that yields increased availability. The approach we've taken for a long time is to power our servers with two independent power lineups. By independent, I mean each lineup has its own switchgear, its own generator, its own UPS, even its own distribution wires. And by keeping these lineups completely independent all the way down to the rack, we're able to provide very high availability and protect ourselves from issues with the UPS. And while we don't love our UPSs for the reasons I've mentioned earlier, this redundancy performs very well. In fact, our data centers running this design achieve availability of almost 7 nines. But if you want to be an amazing operator, you need to constantly push to improve. And as you can see in this peculiar quote, you can't just ruminate about how to make things better, you need to act. So how do we improve our power design? Well, we need to address the big blast radius complicated component, the UPS. And let me show you how we did that. Rather than using a big third-party UPS, we now use small battery packs and custom power supplies that we integrate into every rack. You can think about this as a micro UPS, but it's far less complicated. And because we designed it ourselves, we know everything about it, and we control all the pieces of the software. And as we discussed earlier, this allows us to eliminate complexity from features we don't need, and we can iterate at Amazon speed to improve the design. Now, the batteries can also be removed and replaced in seconds rather than hours, and you can do this without turning off the system. So this allows us to drastically reduce the risk of maintenance we need to do to the battery shelves. The end result, we eliminated a big blast radius, high complexity, failure-prone UPS, and we replaced it with a small blast radius, lower complexity component. Now, this is exactly the sort of design that lets me sleep like a baby. And indeed, this new design is giving us even better availability than what I showed earlier. And better availability is not the only improvement we get from this new design. I'm going to come back to this later when we look at sustainability. But for now, I want to stay on infrastructure. Like the example I showed you here today, we are continually investing in improving the availability of our infrastructure. But we are also aware that no matter how good our infrastructure design and operations, some level of failure is inevitable. Physical events like fires, floods, hurricanes, tornadoes are tangible proof that you cannot achieve extremely high reliability from any single server or even a single data center. After we launched Amazon EC2, availability zones were one of the very first features that we added. At the time, the idea of an availability zone was a brand new concept to most users. But this idea was not new to Amazon, because this is the way we had been running our infrastructure for a long time. About 5 years before we launched AWS, we made a decision to expand the Amazon.com infrastructure beyond the single data centers that we were using in Seattle. Several operational near misses made it clear that we need an infrastructure strategy that allowed us to run our critical systems out of several data centers. One of the leading ideas at the time was to move our system to 2 data centers, one on the West Coast and one on the East Coast. This is the availability model used by most of the world at that time, and it's still common today. And while this idea seems compelling at a high level, it loses its charm quickly when we get into the details. Amazon is a highly stateful, real-time application that needs to do things like keep inventory information up to date and consistent while all the users are accessing the website. And when you're trying to keep data that changes this rapidly synchronized with either strong or eventual consistency, latency matters. With a synchronous strategy, the latency between your replicas will directly impact your maximum transaction rate. And with an asynchronous strategy, the higher the latency, the more out of date your replicas will be. And for Amazon, where millions of customers are accessing real-time inventory information and making real-time changes to that information, neither a low transaction rate nor out-of-date information is acceptable. And this problem isn't unique to Amazon. All modern high-scale applications need to support high transaction rates and seek to provide up-to-date information to their users. So the obvious solution is to run from multiple data centers located closer together. But how close? Like all good engineering challenges, we have a trade-off. The further apart you put 2 data centers, the less likely they'll be impacted by a single event. On one extreme, if you put 2 data centers across the street from one another, it's pretty easy to think about things that might impact both data centers. Common things like utility failures, to less common things like fires and floods, to unlikely but really scary things like tornadoes. But as you get further apart, the probability of these sorts of natural disasters goes down quickly. And once you get to miles of separation, even natural disasters like hurricanes and earthquakes are unlikely to have a significant impact on both data centers. Now you can keep going, but after a while, you need to start imagining some absurdly low probability disasters, things that haven't happened in any of our lifetimes, to imagine simultaneous impact. And of course, on the other side, adding distance adds latency. The speed of light's a pesky little thing, and no amount of innovation speeds it up. Here I've added some estimates for how much latency would be observed as we move our data centers farther apart. The conclusion we came to is that for high availability applications, there's a Goldilocks zone for your infrastructure. When you look at the risk, the further away the better, but after a handful of miles, there's diminishing returns. This isn't an exact range. Too close varies a little based on geographic region. Things like seismic activity, 100-year floodplains, probability of large hurricanes or typhoons can influence how we think about too close. But we want miles of separation. And what about too far? Here we look at the latency between all the availability zones in the region, and we target a maximum latency round trip of about 1 millisecond. Now, whether you're setting up replication with a relational database or running a distributed system like Amazon S3 or DynamoDB, we've found that things get pretty challenging when latency goes much beyond 1 millisecond. I just spent a bunch of time giving you insight into how we think about availability zones. But really, this is not news. You can read all about this in our documentation. Here you can see how we define regions and availability zones. Of particular note, you'll see that each region has multiple availability zones. And we clearly state that every availability zone is physically separated by a meaningful distance. Seems pretty straightforward. But let's see how some other cloud providers talk about their availability zones, and more importantly, let's look at what they don't say. Here's the way other US cloud providers talk about availability zones. Neither provider is clear and direct about what they mean. Words like usually and generally are used throughout their documentation. And when you're talking about protecting your application with meaningful separation, usually and generally just aren't good enough. But the most concerning thing about this documentation is what it doesn't say. Neither provider says anything about how far apart their availability zones are. 2 rooms in the same house are separate locations, but that's not what you want from your availability zones. And another challenge is the fine print. One provider says that availability zones are generally available in select regions. Well, what's a select region? I took a quick look to figure out how many regions that might be. And it looks like about 12 regions have availability zones, and another 40 regions do not. And notably, none of the regions in South America, Africa, or the Middle East have availability zones. It also appears that countries like China and Korea lack regions with availability zones entirely. For most customers, properly designed availability zones provide a powerful tool to cost-effectively achieve very high availability. We believe that availability you can achieve from properly designed availability zones is sufficient for the vast majority of workloads. But some customers require even higher levels of assurance. For example, to meet regulatory requirements. And for these workloads, AWS offers the option to run applications in multiple geographic regions to attain even higher fault tolerance and disaster isolation. But here too, we think about things a little differently. When thinking about things that can impact your services, we naturally think about fires, floods, tornadoes. But humans are the most likely source of a problem, and it's usually well-intentioned humans. As the quote here tells us, anything that a human can touch, a human can muck up. And that's why AWS goes to extreme lengths to protect our infrastructure and our services from human and natural disasters. Anything that can impact them from a single event or a single change. We do this everywhere, but AWS regions are special. Regions are designed to be entirely isolated from one another at the infrastructure level and also at the software and the services level. By default, all AWS services are built and deployed separately to every AWS region to assure that we do not have operational issues across multiple regions simultaneously. A small number of services provide cross-region capabilities. For example, you can use the same AWS credentials to log into 2 different regions. These capabilities are limited, highly scrutinized, and carefully managed. As a result, in our 15 years of operation, services like Amazon S3, Amazon EC2, and Amazon DynamoDB have never had significant issues in multiple regions at the same time. AWS currently has 24 independent regions, each with multiple well-designed availability zones. This year, we're delighted to launch AWS regions in Cape Town, South Africa, and Milan, Italy. We've also announced new regions coming in Switzerland, Indonesia, and Spain. And we'll be adding our second regions in India, Japan, and Australia. The last one was just announced earlier this week. Of course, great availability is not just about keeping everything running. For a cloud provider, it also includes providing you with the capacity you need, when you need it, and where you need it. Just like a technical design, a supply chain is made up of components, or in this case, suppliers. And each of these components can fail. These failures can be caused by short-term issues like labor strikes or fires, or longer-lasting issues like trade disputes. No year in recent memory has seen more disruption than 2020. Starting in March of this year, we saw varying degrees of disruption all over the world as local communities responded to the coronavirus. The impact has been different based on location and time, but unexpected delays and closures were the norm, and in many ways they continue to be. To deal with the real world, the best protection is engineering your supply chain with as much geographic and supplier diversity as you can. Like separation can protect your infrastructure, it can also protect your supply chain. And this has been an area of continued focus for us over the last decade. Here's a view of our supply chain for 4 critical components. Each dot represents 1 or more suppliers. A bigger dot represents more suppliers. At this time, we had a total of 29 suppliers in 4 countries for these 4 components. Now, this is reasonable supplier diversity, but we wanted to do much better. Here's the global supply map for those same 4 components in 2020. Since 2015, we've nearly tripled the number of suppliers and increased our supply base to 7 countries. And this added diversity was a big help in navigating the challenges of 2020. Our investments in a geographically diverse supply chain and our operational focus that we put on capacity planning meant that despite all the challenges of this last year, our customers were able to keep scaling without interruption. It's so satisfying to see how those investments allowed us to help our customers through this challenging time. Now, I want to introduce one of our customers that had to quickly reinvent how they did business when COVID hit this spring. Here is Michelle McKenna, Chief Information Officer for the National Football League.
Thank you, Peter. Our 32 teams and their passionate fans make the NFL America's largest sports organization. Last season, we finished our 100th season with over 15 million viewers per game, creating 41 of the top 50 broadcasts in the U.S. As CIO, I oversee the league's technology strategy, which includes making sure we leverage the best and greatest in new technologies to evolve our game, engage our fans, and protect and develop our players. In early March of this year, we were preparing for the NFL Draft, a live event where we welcome our newest players. The NFL Draft is about conducting the business of football, but it has now also grown into one of our marquee events, enjoyed by hundreds of thousands of fans over 3 days in an NFL city, and even watched by millions online and on television. The 2020 draft was to be in Las Vegas. But like the rest of the world, we learned about COVID-19, and we rapidly began to understand that the event would be much different in 2020. On March 13th, our offices shut down, and the offices and facilities of our clubs soon followed suit. On March 24th, we had a meeting. I recently looked back at my calendar, and it was aptly named Draft Contingencies. And my, what a contingency we ended up needing. By then, we had learned that we would not be able to gather in our facilities at all. So 5 weeks out, the league had to call an audible. The draft was officially going virtual. In the span of a few days, we went from a live broadcast in Las Vegas to hopefully being able to gather in our facilities, coaches and staff, to ultimately everyone, every player, prospect, every coach, general manager, scout, and even our commissioner would need to be remote from their homes. The challenge was immense, with hundreds of questions about how we were going to pull it off. Would we really be able to do it remotely? Could it be done without technical interruption? I remember holding my breath when asked that question by our commissioner, because typically televised broadcasts require a production truck and the reliability of satellite, which rarely fails, transmitted back to studios for production. But this traditional route wouldn't work for all of the hundreds of remotes that we would need. So we had to figure out a new plan. We quickly got together with our partners in events, and one of the first companies we reached out to for help was AWS. The NFL and AWS have been strategic partners for many years now. And as the CIO of the league, I have leaned on AWS many times to help me solve things and challenges that we haven't done before. So right away, I reached out to my partners. Our head of technology, John Cave, actually suggested to us all on a big video call that perhaps we could carry the broadcast over the internet using AWS and mobile phones instead of broadcast satellites and high-end broadcast cameras. At first, it seemed impossible. ESPN, I recall, told us we've never done anything like this before. We had 85 draft picks to do, an even larger number of coaches, GMs, and staff, and we were scattered all over the country. How could this possibly work? Well, with ESPN, our broadcast partner, and AWS, we put our heads down and came up with a plan. Each player would receive 2 devices, one always-on device that would show the emotion of the moment, the anticipation, and the excitement. It was actually the live from the living room shot, so to speak. And the other interview camera would be used for interviews so that a player could step aside and have one-to-one interactions with their new teams, fans, and our commissioner. We created and shipped nearly 200 at-home production booths for top prospects, coaches, teams, and personnel, including everything from 2 mobile phones to lighting to microphones and tripods. And even further than this, we went through a full tech analysis of each location to ensure that if connectivity needed upgrading, it could be done in advance. And we also had every internet service provider on speed dial.
It's Jordan Love from Utah State University.
We're at the house, getting ready for the virtual draft.
This morning I received my draft kit.
Got my whole setup.
This is where I'll be sitting.
Hope everyone's staying home, staying strong.
Can't wait to see everybody on Thursday night.
We were also able to implement a fundraising platform that raised over $100 million for COVID relief. Knowing that this draft could have that kind of impact is really what pushed our teams to keep working forward through this technical challenge so that we could pull this off, ultimately leaving a legacy in the league's history. AWS is a strategic partner and known to be a resilient cloud. And we knew if any organization could help us pull this off, it would be AWS. AWS deployed several of their top engineers to help us think through how we could simultaneously manage thousands of feeds to flow over the internet and up to ESPN in Bristol, Connecticut to put on the air. In order to make that successful, the IT team had to become somewhat of an air traffic controller for a live broadcast. But we also had to see problems in the broadcast ahead of them happening, utilizing the best in the crystal ball technology. You know, seeing the future, something that I know you all have to do. The always-on video feeds were sent to EC2 instances running media gateways. ESPN pulled the feeds from EC2 and produced the show live. The NFL on-premise systems also received the feeds via Direct Connect for our own internal use, which included monitoring and archiving. We used AWS Shield Advanced, a dedicated service to monitor traffic real-time and mitigate attacks, to enhance protection of the NFL media gateways. We used multiple availability zones to minimize impact in the event of a failure, and just in case, even more contingencies, we had additional infrastructure ready to go in another region. AWS helped monitor and alert us when problems were around the corner, using that crystal ball so that we could react in time for live television. It's one thing to be resilient in your day-to-day technology operation, and a totally different thing to be resilient when you are live. This was my first live television experience, and I can tell you it is not for the faint of heart. The AWS cloud infrastructure was the resilient backbone that helped us move thousands of feeds. Many people called this draft special, and it was special indeed. Raising over $100 million, the draft also had a record number of viewers, over 15 million tuning in for the first round picks, a 37% increase from the prior year, and totaling 55 million viewers over the course of a 3-day event. What resulted by chance was the personal connections to the commissioner, prospects, owners, GMs, and head coaches. Social media was a testimony to our fans' involvement. Platforms were buzzing everywhere about every topic. Even our commissioner's jar of M&Ms became a subject of discussion, something that we could never have imagined. But at the core of all this madness, what was so special is how our fans were able to connect with the NFL. You see, they were going through much the same thing we were all going through. They were able to relate to what they were watching. All the people at home were going through the same thing as we were, coping with a pandemic, remote working with your families around, pets, and many distractions. This intimate interaction could not have been planned for, and that's what made it so special and real. The 2020 virtual draft will have long-lasting effects. How we plan and produce our broadcast is going to forever change, and we will now always have, I believe, some virtual components to our draft. For example, our commissioner was able to personally welcome almost every player to the NFL instead of a select few that get to attend a live event. Going forward, we will continue to push and use AWS's cloud to enable and transform our broadcasts and events. Thank you.
Thank you, Michelle. It's great to hear how the NFL and AWS work together to deliver a special and successful NFL draft. The last couple years, I've talked a lot about our investments in AWS Silicon. That's because these investments have been allowing us to deliver differentiated performance, exciting new features, improved security, and better power efficiency for AWS customers. We're going to look now at how we design our chips. But chips are only part of this story. What's really exciting and transformative about deep investments in AWS Silicon is being able to work across custom hardware and software to deliver unique capabilities. And by working across this whole stack, we're able to deliver these improvements faster than ever before. At AWS, we've been building custom hardware for a very long time. Our investments in AWS Custom Silicon all started in 2014, when we began working with a company called Annapurna Labs to produce our first custom Nitro chip. Shortly after this, Annapurna Labs became part of AWS and is now the team working on all of these exciting chips. Now, we use that Nitro chip I just talked about to create specialized hardware, which we call the Nitro controller. We use the Nitro controller to turn any server into an EC2 instance. The Nitro controller runs all the code that we use to manage and secure the EC2 instance and virtualize and secure our network and storage. And by running on the Nitro controller rather than on the server, we're able to improve customer instance performance, increase security, and innovate more quickly. Today, I have an example that I believe really brings this to life. Last week, we announced the Amazon EC2 Mac instance. There was a ton of excitement about this launch. But how do you make a Mac into an EC2 instance? Well, here you can see an actual Mac EC2 server. You probably recognize the Mac Mini in the middle of the server tray. And if we pan out a bit, you'll see the Nitro controller. The first Mac EC2 instance is the marriage of a Mac Mini and a Nitro controller. And as you see, we did not need to make any changes to the Mac hardware. We simply connected a Nitro controller via the Mac's Thunderbolt connection. When you launch a Mac instance, your Mac-compatible AMI runs directly on the Mac Mini, no hypervisor. The Nitro controller sets up the instance and provides secure access to the network and any storage you attach. And that Mac Mini can now natively use any AWS service. It can have multiple network ENIs, it can attach high-performance encrypted EBS volumes, it can have instance firewalls, and the instance has low latency access to other AWS services like Amazon S3 and Amazon Aurora. All the great stuff that comes with being an EC2 instance. And because all of this happens outside the Mac Mini, you get all the resources of the Mac dedicated to your workload, just as you would if that Mac was running on your desktop. Today, we're on our 4th generation of custom Nitro chips. And each generation of Nitro chip has enabled improved performance. The most recent generation of our Nitro chip is powering the recently announced C6GN instance. The C6GN is our highest performing network optimized EC2 instance. It's specifically designed for the most demanding network workloads, including high performance computing. Now, there are lots of different ways to look at network performance, and the C6GN improves performance on all of these dimensions. But as I've discussed a few times in past keynotes, achieving lower latency with reduced jitter is one of the hardest problems in engineering. Latency is one of those challenges that cannot be solved with more transistors, more engineers, more power. So here you can see the C6GN instance and how it reduces round-trip latency significantly compared to the C5N. The C5N was previously our best performing instance for network-intensive workloads. And improvements like this aren't just at the average. You can see the improvement in the tail latency as well. And this means reduced performance variability, which for scale-out applications means better overall performance. We're going to look at this more in a minute. Now, while we're very excited about the Nitro chips and our investments here, our investments in AWS custom silicon extend far beyond Nitro. Last year, we released our first machine learning chip, AWS Inferentia. We targeted inference with our first chip because most at-scale workloads, machine learning workloads, the cost of the inference represents the vast majority of the cost. And for Inferentia provides the highest throughput at almost half the cost per inference when compared to GPUs, which are commonly used for large-scale inference infrastructure. Our AWS Neuron team developed a software to allow machine learning developers to use Inferentia as a target for popular frameworks, including TensorFlow, PyTorch, and MXNet. With Neuron, they can take advantage of the cost savings and performance of Inferentia with little or no change to their ML code, all while maintaining support for other ML processors. We've been delighted by the results customers have achieved in migrating their large-scale inference workloads to Inferentia. Amazon Alexa recently moved their inference workload from NVIDIA GPU-based hardware to Inferentia-based EC2 instances and reduced cost by 30%, while achieving a 25% improvement in their end-to-end latency. And as you can see, many other customers are reporting great results. And while we're excited by the results customers are seeing with Inferentia, our investments in machine learning chips is just beginning. Last week, Andy announced AWS Trainium, our second machine learning chip. Like Inferentia has done for inference, Trainium will provide the lowest cost and highest performance way to run your training workloads. I'm looking forward to showing you more technical details about Trainium next year. But today, I want to talk to you about our third area of silicon investment, AWS Graviton. We introduced Graviton a couple years ago with the Graviton-based A1 instance. Our purpose with that instance was to work with our customers and our ISV partners to understand what they needed to run their workloads on a modern 64-bit ARM processor. We learned a lot about how to make it easy for customers to port and run applications on Graviton. This year, we released Graviton2. I didn't get a chance to tell you about it at last year's keynote, but the good news is I can now get into the details of Graviton2, how we designed it, and more importantly, show you some of the amazing results that our customers are seeing moving their workloads to Graviton2. With Graviton2, we set out to design the best performing general purpose processor. And while we wanted the best absolute performance, we also wanted the lowest cost, faster and less expensive. Having lofty goals for multi-$100 million project like a new chip isn't unusual. What's unusual is exceeding these goals. Graviton2 is the best performing general purpose processor in our cloud by a wide margin. It also offers significantly lower cost. And as I will show you later when I update you on sustainability, it's also the most power efficient processor we've ever deployed. Great results like this require amazing execution, but they also require a clever plan. Taking the same path as every other processor would not have delivered the type of performance we're seeing here. Our plan was to build a processor that was optimized for AWS and modern cloud workloads, taking full advantage of the Nitro architecture that I talked about earlier. So what do modern cloud workloads look like? Well, to understand that, let's start by looking at what a modern processor looks like. Before about 15 years ago, the main difference between one processor generation and the next was the speed of the processor. And this was great while it lasted. But about 15 years ago, this all changed. New processors continued to improve their performance, but not nearly as quickly as they had in the past. Instead, new processors started adding cores. And now you can think of a core like a mini processor on the chip. Each core on the chip can work independently and at the same time as all the other cores. And this means that if you can divide your work up, you can get that work done in parallel. Processors went from 1 core to 2 and then 4. The trend was obvious and exciting. So how did workloads adapt to this new reality? Well, the easiest way to take advantage of cores is to run more independent applications on the server. And modern operating systems have gotten very good at scheduling and managing multiple processes on high core systems. Another approach is multi-threaded applications. Multi-threaded applications allow builders to have the appearance of scaling up while taking advantage of parallel execution. Languages like Java make multi-threaded programming easier and safer than the C++ that I grew up with. But modern languages like Go, Erlang, and Rust have completely changed the game for high-performance multi-threaded application development. To me, one of the most exciting trends is the move to services. Service-based architectures move us from large monolithic applications to small, purpose-built independent services. This is exactly the type of computing that containers and Lambda enable. Taken together, you can call these trends scale-out computing. And while scale-out computing has evolved to take advantage of higher core processors, processor designers have never really abandoned the old world. Modern processors have tried to have it both ways, catering to both legacy applications and modern scale-out applications. And this makes sense if you think about it. As I mentioned, producing a new processor can cost hundreds of millions of dollars. And the way you justify that sort of large upfront investment is by targeting the broadest adoption possible. The more processors you ultimately end up producing, the less significant that upfront cost is to each incremental processor produced. So modern many-core processors have unsurprisingly tried to appeal to both legacy applications and modern scale-out applications. Processor designers have been constantly adding functionality to their cores for decades. With legacy workloads, you need to assure that every core never stalls while waiting for resources. So you end up adding more and more of everything, and everything gets bigger. And somewhere along the way, a funny thing started happening. Cores got so big and complex that it was hard to keep everything utilized. And the last thing you want is transistors on your processor doing nothing. So to work around this limitation, processor designers invented a new concept called simultaneous multithreading, or SMT. SMT allows a single core to work on multiple tasks. Each task is called a thread. Threads share the core, so SMT doesn't double your performance, but it does allow you to take use of that big core and maybe improves your performance by 20 or 30%. But SMT also has drawbacks. The biggest drawback of SMT is it introduces overhead and performance variability. And because each core has to work on multiple tasks, each task's performance is dependent on what the other tasks are doing around it. Workloads can contend for the same resources like cache space, slowing down the other threads on the same core. In fact, workloads like video transcoding and high-performance computing, which spend a lot of time optimizing their code for scale-out workloads, disable SMT entirely because the variability introduced by SMT makes their applications run less efficiently. And while you can turn off SMT, you can't reclaim the transistors that you used to put it in there in the first place. And this means you're paying for a lot of idle transistors. There are also security concerns with SMT. SMT is the main vector that researchers have focused on with so-called side channel attacks. These attacks try to use SMT to inappropriately share and access information from one thread to another. Now, we don't share threads from the same processor core across multiple customers with EC2 to ensure customers are never exposed to these potential SMT side channel attacks. And SMT isn't the only way processor designers have tried to compensate for overly large and complex cores. The only thing worse than idle transistors is idle transistors that use power. So modern cores have complex power management functions that attempt to turn off or turn down parts of the processor to manage power usage. The problem is, these power management features introduce even more performance variability. Basically, all sorts of things can happen to your application, and you have no control over it. And if you're a system engineer trying to focus on performance, this can be extremely difficult to cope with. And in this context, you can now understand how Graviton2 is different. The first thing we did with Graviton2 was focus on making sure that each core delivered the most real-world performance for modern cloud workloads. When I say real-world performance, I mean better performance on actual workloads, not things that lead to better spec sheet stats like processor frequency or performance micro-benchmarks, which don't capture real-world performance. We used our experience running real scale-out applications to identify where we needed to add capabilities to assure optimal performance without making our cores too bloated. Second, we designed Graviton2 with as many independent cores as possible. When I say independent, Graviton2 cores are designed to perform consistently. No overlapping SMT threads, no complex power state transitions. Therefore, you get no unexpected throttling, just consistent performance. And some of our design choices actually help us with both of these goals. Let me give you an example. Caches help your cores run fast by hiding the fact that system memory runs hundreds of times slower than the processor. Processors often use several layers of caches. Some are slower and shared by all the cores, and some are local to a core and run much faster. With Graviton2, one of the things we prioritized was large core local caches. In fact, the core local L1 caches on Graviton2 are twice as large as the current generation x86 processors. And because we don't have SMT, this whole cache is dedicated to a single execution thread and not shared by competing execution threads. And this means that each Graviton2 core has 4 times the local L1 caching as SMT-enabled x86 processors. All of this means each core can execute faster and with less variability. Okay, now hopefully you have a pretty good idea of what we focused on when we designed and built Graviton2. Let's look at how things turned out. Here's a view of how many execution threads were available when we built in our processors that we used to build our C instances over the years. On the left, you see our C1 instance, which was launched with the processor that had 4 threads. And on the right, you see Graviton2 with its 64 execution threads, which is used in the C6G. Now, when you look at this graph, this looks like pretty incremental progress. But remember, this view is threads, not cores. So for most of these processors we're looking at, those threads have been provided by SMT. Let me adjust the graph and let's look at real cores. Okay, now you can see how Graviton2 really differentiates itself. That's a significant nonlinear improvement. So let's look at some benchmarks. Because Graviton2 is an ARM processor, a lot of people will assume that Graviton2 will perform good at front-end applications. But they doubt it can perform well enough for serious I/O-intensive back-end applications. But this is not the case. So let's look at a Postgres database workload performing a standard database benchmark called HammerDB. First, we're going to look at the M5 instance. Now, the smallest M5 instance has 2 execution threads. It's 1 core, but 2 threads. Remember I mentioned we don't share cores across customers, so we can only scale down to 2 threads. And our largest M5 instance actually has 96 threads. But that's actually 2 processors on the same system. And that's going to cause some problems. So we're going to start by looking at just how this benchmark performs on 1 M5 processor. OK, here you can see we get pretty good scaling. As we add more threads, things improve almost linearly. Not quite, but pretty close. OK, now I'm going to add the larger M5 instance sizes. This is the threads from the other processor. OK, you can see right away scaling here isn't nearly as good. And there's a few reasons for this flattening. But it mostly comes down to sharing memory across 2 different processors. And that sharing adds latency and variability to the memory access. And like all variability, this makes it hard for scale-out applications to scale efficiently. Let's add Graviton. Here we can see the M6G instance on the same benchmark. You can see that M6G delivers better absolute performance at every size. But that's not all. First, you see the M6G scales almost linearly all the way up to the 64-core largest instance size. And by the time you get to 48 cores, you have better absolute performance than even the largest M5 instance with twice as many threads. And you can see M6G offers a 1-core option. Because the M6G doesn't have threads, we can scale all the way down, giving you an even more cost-effective option for your smallest workloads. And for your most demanding workloads, the 64-core M6G instance provides over 20% better absolute performance than any M5 instance. But this isn't the whole story. What we're looking at here is absolute performance. Things get even better when we factor in the lower cost of the M6G. Let's look at that. OK, here you can see the biggest and smallest M6G instance compared to the corresponding M5 instance variants on the same cost per operation basis for the benchmark we just looked at. You can see the largest size instances are nearly 60% lower cost. And because the M6G scales down better than a threaded processor, you can save even more with the small instance, over 80% on this workload. Of course, benchmarks are exciting, but what's really exciting is seeing customers having success using Graviton2. And the benchmarks that really matter, customer workloads, are showing the performance and price benefits we expected. I got a chance to catch up with one of those customers, Jerry Hunter, who runs engineering for Snap, about some of the benefits they're seeing from AWS and Graviton2. Jerry actually ran AWS infrastructure before he took his current job at Snap about 4 years ago. So it was fun to catch up with Jerry. Let me share a little bit of our conversation. Jerry, great to see you. When we talked about doing this, I thought we might be in Vegas and we might be able to have a beer afterwards. don't think that's going to happen, but it's still great to catch up with you.
Nice to be here.
Awesome. Well, today I spent a little time talking about Amazon culture. So let's start there. You were at Amazon for almost 10 years. Can you tell me, is there anything you learned at Amazon that you took with you to Snap?
Yeah, I actually think operational discipline, and I'll call it operational discipline. That's the leaders are deep in the details, both technology and operationally, of the space that they're running. One of my favorite stories is like when I first started at Snap, we were trying to understand cost. And as we grew, our costs were going up. There was a tactic that we used at AWS that I really liked, and that was understanding how to take the cost and associate the unit of cost with the value you're giving to your customer. So that unit cost associated with what the customer is buying. And it turns out that it not only works inside of AWS, but it works for people that are using AWS. So we look at the services that we're offering to our customers in terms of the value they get, and then scale it, aggregate all of those different services we're using to describe the cost associated with the thing we're delivering. And then I hand that over to the engineers, and it gives the engineers observability into how costs are being spent and where there's an opportunity to tune costs. So that cost efficiency comes straight out of the metric. And that's turned out to be a real help for us on our path to profitability.
Awesome. Well, you are one of the best operators I know, so it's great to hear you've taken that with you. But while we're talking about your time at Amazon, why don't you tell us about something you did here that maybe not everybody knows about that you're proud of?
Yeah, there's a lot of stuff I was proud of. There's a lot of firsts, but this one's really easy for me. When we worked on renewable power, I still am satisfied by the work that we did there. It was deeply satisfying, and here's why. It was complicated. The laws that you have to understand and follow for putting power on the grid are Byzantine. And building wind farms and solar farms is new, and it's new technology, and there's all these different ways to do it. And so there was a lot of firsts, and it was really fun. I also think that there are things I learned about renewable power that I think AWS knows now that would be useful to the rest of the world, because it's a powerful thing to be able to deliver power and know that it's being done productively.
Yeah. Well, we are definitely appreciative of that early work you did with renewable power. We've come a long way, but like anything, you build on the success of the past. That's actually a big part of what the Climate Pledge is all about for us. It's how we can help other companies and work together and solve all of these problems that we have to solve. So I'm looking forward to giving an update on that. But let's get back to Snap. So tell me about Snap.
Sure. Snap's the company that builds the Snapchat app. It's the fastest and easiest way to communicate with friends and family through the camera. Every day, 250 million people around the globe use Snapchat to send 4 billion snaps. That's billion with a B, to either communicate, tell stories, or use our augmented reality. And we care deeply about our customers' privacy. So we have a privacy-first engineering focus, and we do things like messages and snaps that disappear by default. We have curated content that comes from trusted partners rather than an uncurated, unmoderated newsfeed. And I think lastly, we care deeply about innovation.
Very exciting. So tell me about how Snap's using AWS.
Well, we use EC2 and Dynamo and CloudFront and S3, and we try just about everything. We use it because it allows us to control costs, and I don't have to spend engineers on building infrastructure. I can spend them on doing features, which is what allows us to provide value to our customers. And we get to use new innovations from AWS like Graviton and reduce costs, create better performance for our customers with not a lot of energy.
Awesome. Well, I'm excited to hear you're using Graviton. One of the things that customers always worry about is how difficult it's going to be to move to Graviton. Can you tell me what your experience was there?
Yeah, we found it pretty straightforward. The APIs are pretty similar to what we were using before, so it didn't take a lot for us to migrate our code over to test it out. We started trying it out with some of our customers to see how it worked. We liked the results, so we rolled it out into the fleet and immediately got like a 20% savings, which is fantastic, because we were able to switch this load over and immediately get that cost savings and get higher performance.
Awesome. Glad to hear you're getting that value from Graviton. But what else besides cost and performance do you value about AWS?
Well, when I was at AWS, I spent a lot of personal time thinking about how to make things more secure. And I know that everybody at AWS does that. It's a huge point of value for us. As I've just said, we care deeply about privacy and security, and that allows us to spend our time. My security team, which I love, they do a great job, focus on the part of the app that we own. We don't have to spend time worrying about what's happening in the cloud because we know it's being done for us by people who are really excellent. So I personally appreciate that. It's something that brings me comfort at night when I go to bed. The other thing that I really like is that AWS is in regions all over the world. You know, early days, we had our backend as a monolith in a single region in the middle of the country. And so if you were in Frankfurt, for instance, and you were communicating with somebody that was also in Frankfurt, those communications had to travel all the way back to the US through undersea cable, blah, 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 and make its way back to that person. Well, there's a speed of light thing there, and so it could be clunky and slow. And this is the conversation. If you're not speaking quickly, it doesn't feel like a conversation. So bringing all of that to a data center in, say, Frankfurt or in India or Sydney gives us real-time access to that speedy tech that our customers expect.
Awesome. Well, it sounds like you're making good use of AWS, but what's next for Snap?
Well, there's a ton of stuff that we're working on, but there's two things I care deeply about right now. The first is we're on a path to profitability, and we're making good progress. I could never make that progress if I was building my own data centers. And so it's super useful for me to try things like we did with Graviton, turn them on and find immediate cost savings. So I'm pretty happy about the path we're on. I'm happy about the partnership that we have and getting there. And the second thing is AWS keeps innovating, and that lets us keep innovating. And I can't hire enough people to do all the innovation that I want, which, by the way, I'm hiring. But you know, we test just about everything that comes out from AWS, and I look forward to continued innovation from AWS because there's a lot of innovation you should expect to see coming out of us over the next few years, which I'm not going to talk about what it is, but I'm very excited about it, and I'm really looking forward to our partnership together to deliver that.
Well, I'm disappointed that you didn't give away any secrets, Jerry, but I'll have to leave it at that. I really appreciated this chance to catch up, and I'm looking forward to when we can actually see each other in person.
Oh, me too. Counting on it.
It was really nice catching up with Jerry and hearing about the great work he's doing at Snap. And you heard us talk about the early work that he did on renewable energy many years ago. And now I'm really excited to give you an update on where we are now. Last year, we announced the Climate Pledge, which commits Amazon and other signatories to achieve net zero carbon by 2040, 10 years ahead of the Paris Agreement. The Climate Pledge is not just one company's climate commitments. It offers the opportunity to join a community of leading businesses committed to working together as a team to tackle the world's greatest challenge, climate change. Including Amazon, 31 companies have now signed the Climate Pledge, including Verizon, Rivian, Siemens, and Unilever. Today, I'm going to give you an update on the investments we're making in AWS to support the Climate Pledge, as well as some of our other sustainability efforts. Because power is such an important part of AWS's path to zero net carbon, let's start there. I'm going to give you an update on our path to 100% renewable energy here, but first, I want to talk about efficiency. The greenest energy is the energy we don't use. And that's why AWS has been and remains laser focused on improving efficiency in every aspect of our infrastructure. From the highly available infrastructure that powers our servers, to the techniques we use to cool our data centers, to the innovative server designs we use to power our customers' workloads, energy efficiency is a key part of every part of our global infrastructure. We actually looked at two innovations earlier today. First, we talked about how we removed our central UPS from our data center design. What we didn't talk about was how this improved our power efficiency. Every time you have to convert power from one voltage to another, or from AC to DC, or DC to AC, you lose some power in the process. So by eliminating the central UPS, we were able to reduce these conversions. And additionally, we've spent time innovating and optimizing the power supplies on the racks to reduce energy loss in that final conversion. Combined, these changes reduced our energy conversion loss by about 35%. We also talked about Graviton2, and I mentioned it was our most power-efficient processor. In fact, Graviton2 processors provide 2 to 3.5 times better performance per watt or energy use than any other AWS processor. This is a remarkable improvement in power efficiency. With the world's increasing need for compute and other IT infrastructures, innovations like these are going to be critical to assuring that we can sustainably power the workloads of the future. And AWS's scale and focus on innovation allow us to improve efficiency faster than traditional enterprise data centers. According to a 451 research, infrastructure that AWS operates is 3.6 times more energy efficient than the median surveyed US enterprise data center. And this study was based on infrastructure before the innovations I just talked about. So this gap is only going to widen. And when you combine AWS's continuous focus on efficiency with our renewable energy progress, customers can achieve up to 88% reduction in carbon emissions compared to using an enterprise data center. So let's look at that renewable energy progress. During my keynote in 2018, I showed you the large-scale utility wind and solar projects that we were building to power our data centers. At the time, we had added over 900 megawatts of new wind and solar in the United States. In addition, Amazon also deployed solar on our rooftops in our sort centers and distribution centers across the world. Last year, we announced 14 new wind and solar projects, adding approximately 1,300 megawatts, including our first renewable projects outside the United States, in Ireland, Sweden, the United Kingdom, Spain, and Australia. But I also mentioned that we were just getting started. So far this year, we've announced 700 megawatts of new wind and solar farms, including our first renewable project in China. Even with the challenges of COVID-19, our projects in Sweden and Spain went into operation. And today, we have much more to share. We're proud to announce more than 3,400 megawatts of additional renewable energy projects, including our first projects in Italy, France, South Africa, and Germany. These projects will bring Amazon's 2020 total buy to nearly 4,200 megawatts of renewable power across 35 wind and solar farms. Sound impressive? It is. Amazon's renewable energy procurement in 2020 is the largest by a corporation in a single year, exceeding the record by 50%. It's also a 300% increase over the projects we announced last year. And this progress is a big part of why we now believe we're on track to hit our 100% renewable energy goal by 2025, 5 years ahead of our initial target of 2030 that we shared last year. Our focus on energy efficiency and renewable power delivers significant progress on AWS's sustainability journey. However, to meet Amazon's climate pledge commitment to reach zero net carbon by 2040, we have to reduce a broad category of emissions, and these are known as Scope 3 indirect emissions. As that name implies, these emission sources are not directly controlled by us, but they still result from our business operations. All businesses have these sorts of emissions, and they include things like employee travel and office expenses. For AWS, our largest source of indirect carbon emissions come from constructing our data center and manufacturing of our hardware. Our sustainability, engineering, construction, and procurement teams are hard at work on these problems. For example, cement production is responsible for 7 to 8% of the world's carbon emissions, largely due to a process to make a cement ingredient called clinker. The process to make clinker was patented almost 200 years ago, and it's still widely used because it's cheap, it's reliable, and it produces high-quality concrete. Clinker is made by grinding limestone and combining with other materials and then processing it at very high heat. This processing produces large amounts of carbon emissions, both from the burning of fossil fuels to process it, as well as the gases released from the chemical reactions during the production process itself. And concrete is critical for so many different types of building and infrastructure in modern life. Things like buildings and highways, bridges, dams, schools, hospitals. Concrete is everywhere. Most of the world's concrete production is used to produce all of this infrastructure, and only really a very small fraction is used to produce data centers. To help you understand the scale, we estimate that all the concrete that AWS used to build data centers last year is far less than the concrete used to build the foundation of the Golden Gate Bridge. But while we're a small part of global concrete usage, we believe we can have an outsized impact on solving a problem that the world so desperately needs to address. So what are we doing? While we can't eliminate concrete, our scale enables us to help drive industry change by creating demand for more sustainable alternatives. In the near term, AWS plans to increase the use of supplementary cementitious materials in the cement that we use for our data centers. These supplementary materials replace the need for the carbon-intensive clinker. One example would be using recycled byproducts from other industrial processes like manufacturing iron and steel. We expect that increasing the amount of these replacement materials can reduce the embodied carbon in a data center by about 25%. Longer term, we'll need solutions beyond these current substitutes, and we're working with partners on alternative clinkers that are made with different processes that result in lower emissions. AWS is also evaluating and experimenting with technologies that produce lower carbon concrete by utilizing carbon dioxide during the manufacturing process. One example is Carbon Cure, which injects carbon dioxide into the concrete during production. This process sequesters or traps carbon dioxide in the concrete, and it also reduces the cement concrete, which further lowers the embodied carbon in the concrete. Carbon Cure is also one of the first companies we invested in with the Climate Pledge Fund, which we announced this last June. This fund, with an initial $2 billion in funding, will invest in visionary companies whose products and solutions will facilitate the transition to a sustainable, low-carbon economy. Amazon's already incorporating Carbon Cure into its construction process in HQ2 in Virginia. And this is just one example of how our commitment to be net zero carbon will drive us to innovate for a lower carbon future. For AWS, running our operations sustainably means reducing the amount of water we use as well. Like concrete, data centers represent a tiny portion of the world's water usage. But our view at Amazon is that we can punch above our weight class on these problems. In many regions, AWS uses outside air for cooling much of the year. And on the hottest days, when we need to use water to help with that cooling, we've optimized our systems to reduce this water usage. With our designs, even on the largest data center running at full capacity, we use about the same water that 25 average US households would use. So as part of this water use, we look for opportunities to return the water that we do use to the communities. And I want to share with you an example of how we partner to deliver water to farmers in our US West region.
My name is Dave Stockdale. I'm the city manager for the city of Umatilla. We're a small farm community out here in Eastern Oregon. 4 years ago, as we were looking at the growth that AWS itself brought to the community, we realized pretty quickly we were going to exceed our capacity at our wastewater treatment facility. We started looking at other creative solutions.
I'm Bo Shills. I'm on the AWS water team. One of the things we do here is we treat the water before it runs through our data center, and then we're able to use it 3 or 4 times. And our cooling water is not dirty.
It just didn't make sense to have clean water run through a very expensive treatment process.
Instead of it going to a wastewater treatment plant, we put it into this canal where it then goes to reach the local community so it can be repurposed for irrigation. In our US West region here in Oregon, we reuse 96% of all of the wastewater we discharge from our data centers.
I'm Vern Fredrickson. I've been growing hay and other irrigated crops in this area for the last 35 years. Besides the land that we own, water's one of the greatest assets that we have in this community. We're glad to see businesses like AWS giving water back to the farming community.
We're very grateful to be able to work with the City of Umatilla and the Port of Morrow to enable this and to be good water stewards in this community.
Every time we reuse water, it's less water we're pulling from our rivers and streams. It's good for the environment, it's good for the economy, it's good for our community as a whole.
In addition to the water we're returning to communities, AWS is working on community water programs all around the world. In 2018, many of you might know that Cape Town, South Africa, nearly ran out of fresh water. One of the problems in Cape Town is that invasive species soak up vast quantities of fresh water. AWS is funding projects to remove these invasive species through a partnership led by the Nature Conservancy. In addition to a data center design in Cape Town that reduces water use, these efforts assure that we are returning far more water to the Cape Town community than we use. We're also working on watershed restoration projects in São Paulo, Brazil, and Amazon is funding water filtration, rainwater harvesting, and groundwater recharge projects that will bring 250 million gallons of water annually to 165,000 people in India and Indonesia. I hope that what I've shared today gives you a sense of the depth and breadth of sustainability efforts at AWS. Teams across AWS are working to increase our efficiency, achieve 100% renewable energy, and reduce carbon intensity in our infrastructure. New technologies, products, and services are required to achieve our goal of net zero carbon by 2040. And we're committed to working with companies across many industries to drive innovation, not just for Amazon and the signatories of the Climate Pledge, but for the world. I want to end today with this exciting fact. As I mentioned earlier, Amazon has announced over 6.5 gigawatts of new renewable energy, with nearly 4.2 gigawatts of this total coming in 2020. And as we announced this morning, this makes Amazon the largest corporate procurer of renewable energy in the world. And as we like to say at Amazon, it's still day one. With that, thank you for participating in this year's very unique reInvent. Stay safe, and I look forward to seeing you in person soon.